So today we're going to be writing some code to show that with explicit differencing, the maximum time step that gives a satisfying solution is 0.5 seconds, so that when you go beyond 0.5 seconds, your values for temperature start turning off towards negative infinity and or positive infinity, depending on the time step. In this case, we're going to be using NumPy and Plotly. It's a pretty simple thing. The main interesting bit is working with lists and arrays. But for now, we're just going to be using NumPy and Plotly. And then this solve banded isn't for this video, but we will be using it in the Craig-Nicholson method that we're doing in video 4 or 5. Can't remember which one it is. But I'm just going to leave that in there for now so I can use the same notebook. And then we have our thermal diffusivity, our time step, and our position steps. We have our value for R, and I'll go over how we kind of came about getting this R. I'm not going to go over all the math with the explicit differencing, but I'm going to just talk about the method and how we got the R, the coefficient R. I'm not really going to go over it though because it's basically just algebra. And then we have our initial temperatures, or our room temperature, and then our left and right temperatures. We are going to be modeling a bar, which I mentioned in video 1. So we're only concerned about one axis, one direction. We don't need to worry about multi-dimensional analyses. But you could scale this up to multiple dimensions pretty easily. So I know I said that I wasn't going to actually write out the explicit differencing, but I've decided to just because it makes everything else a little easier. Thankfully, it's pretty simple in my opinion. But basically, we have this bar, and we have this starting temperature, TL, or left side, and then TR. And I think in this case, it's 50 and 80 degrees, but we're not really concerned about that right now. And what we're concerned about is modeling how the temperature of the bar changes from left to right, and also how it changes over time. So we have the expression alpha times the second partial derivative of temperature with respect to position. Sorry, I've had a bad cough for a few days. It's going to be equal to the first partial derivative of temperature with respect to time. So in explicit differencing, we have set time increments, set position increments that we're using to model the temperature over time instead of doing it as like a continuous function. In this case, and actually I should mention that this makes it really simple to use in Python because it lets us just use arrays or lists to store the values of our temperatures we move through time and position, time and space. So anyways, we're going to have some time step delta x and some position step delta x and some time step delta t. And then to get the actual position we are, or the actual time we are along the bar, you just multiply your time step or your increment by how many increments you've been through. So say we've been through 30 increments, 30 times delta t, and our delta t equals 0.5 seconds. And then we know if we've been through 30 increments, then our actual time is 15 seconds. In this case, we're going to label the time step n and the position step j. So if I was saying if this is position j, the temperature at that position and at the current time is just tj comma n, right? And then if this is j plus 1 increment, this being delta x, that would just be tj plus 1 n. So in this explicit differencing, what we're essentially doing is taking the difference between 2 points, the difference in the temperature between 2 points divided by the increment, and essentially getting sort of an average of the difference in temperatures between those 2 points. So let's do this partial derivative here, the second partial derivative. And the first thing we're concerned about is how the temperature changes going from point j to point j plus 1. So that's just going to look like temperature at j plus 1 comma n minus the temperature at j comma n divided by our or position step. And then we're also interested in the second derivative. The second derivative is just how the first derivative changes. So to change the value of Tj, the temperature at j plus 1 comma n, we have to change the temperature at Tj comma n. And so to get the value at Tj comma n, we have to take the value at Tj comma, j minus 1 comma n. So essentially, we're always looking at the previous position as we go through the bar. So we're going to have Tj comma n minus Tj minus 1 comma n, all divided by delta x. And then this is all over our position increment. And I'm just going to simplify this. So we have the same terms here, and really these are delta x squared. We have these two terms that are the same. These two terms are different, so I'm just going to rewrite this as alpha Tj plus 1 comma n minus 2 Tj comma n, and then these two negatives cancel, so we're going to have plus Tj minus 1 comma n all over delta x squared. And that's going to be equal to our partial derivative of temperature with respect to time. Now we can do the same thing with the time increment, and it's going to look really similar, except instead of varying the position increment, we're varying the time increment. So we're going to have Tj comma n plus 1 minus Tj comma n all over delta t, and we're only concerned about the first derivative, so we don't have to continue on. And then from there we can multiply this across this delta t, so we're going to have alpha delta t, and then this term here is the same as these two terms, so we'll multiply that across. Or you know what, let's just move this denominator out of there. So delta x squared. This is the r that I mentioned before. So we can just rewrite this as r t j j plus 1 comma n minus 1 minus 1 plus, trying to remember, or why am I trying to remember? When we add this across, we're just going to have minus 1 minus 2 r. Forgot we were leaving the r outside for now. J comma n plus Tj minus 1 comma n. And then we can just distribute this r through, and then that's going to be equal to the temperature at the next time step. So that is why we're interested in looking at this explicitly. It makes it really simple to model this as we move through time and space. And sorry, I actually made a slight mistake here. It's not accurate to write this like this, because then you would distribute this r through to this 1. That's not true. So a better way to write this would just be distribute the r through beforehand, and then you end up with this. So the first thing we need to do is make an array for our temperature. And to do that, we need to know how many position steps we're going to have, because we're going to have a row for each temperature in our array, or for each position in our array, I should say. And the way we're going to define the length of the bar is by how many increments we go through to get the full length of the bar. So if the bar is 20 meters and our increment is 1 meter, we're just going to say n equals 20, and then x equals all the steps between 0 and 20 with increment 1. Let me change that then, just so we can change that if we ever need to. And let me go ahead and run these. And then we can make our temperature array. And we want to make a temperature array And for every position increment, we also want to keep the outside temperature the exact same. So in this case, we're going to say we want our temperature array to be an array with the same length as n, and we want it to contain our initial temperatures. So again, all this is doing is setting up an array with 20 increments, and we're pre-filling our outside temperature. And then we want to set our left and right ends, the temperature of our left and right ends. So we're going to say the first position is going to be our left temperature, the left end of the bar. And we're going to say our last temperature, and it's just easier to use -1 since the length of it's just easier to do it that way instead of keeping track of what the last index of the array is. We're going to set that to our right temperature. And then what we need to do is we need to make a for loop that goes through the equations that we just came up with, or the equation, I should say, that we just came up with, and updates those values every time through the for loop. So we're going to go, we're just going to say for I in range 500. And we want to update the temperatures between the second value, not the first value, because the first value is just our initial temperature. We don't need to update that. Or the temperature at the end of the bar, we don't need to update that. And then our last value, and then the very last value of the slice, or our temperature on the right, is not included. So we set it to -1. And then we just have to write out our equation, essentially. So we have R times T, and then we want to take the third index, or really the second value, which would be the J minus 1 in the or J plus 1 in the previous equation, I should say. And then we want to take that all the way through the array. And then 1 minus 2R. And then the same thing, except this time it's J comma N. So we're doing 1, -1. And then we want to do TJ minus 1, or TJ minus 1N, which is going to be all the way through to the penultimate value. And then, sorry, I said penultimate value. I guess I didn't type it out. And then multiply that by R. And then we don't want to make 500 plots of this. So what we're going to do, and actually we're going to start at 1. What we want to do is make a plot every certain number of increments. In this case, let's do every 20 increments. And the way we're just going to do this is by taking our I value, dividing it by some number, and seeing if the remainder is 0. If the remainder is 0, then that means that we're at a multiple of that many increments, and we want to make a plot. So in that case, we're going to do I modulo 20. So in case you're not familiar with module or modulo, good thing I ran that now. Cool. In case you're not familiar with modulo, something like, say, 30 modulo 3. It's going to give a remainder of 0. This 0 is just the remainder of when you divide the left side by the right side. So 30 modulo 4 should give a remainder of 2. Yep. And in that case, we want our the result of our modulo for our I index with our number of increments that we're concerned about. We want that to be equal to 0. And when that is, we're going to make a scatter plot. And it has been a long time since I've done this. So 1 second, I'm going to refresh myself on the syntax and we'll get right back to it. So while I was out checking the syntax guide, and let me rerun this so you don't see our final creation, I ran into a lot of problems with the graph as I was trying to make it. And it turns out that if you choose not to type in these decimals to specify that it's a float, you run into a lot of issues. So I should have listened to Carlos and just added that extra period, and it would have saved me a lot of time. But anyways, looks like my initial thought was correct. x equals x, this x being this array that we set up earlier for all the increments along our x-axis. And then our y is just our temperature. And our mode equals lines. And then before that, we also want to have our initial scatter plot. And of course, we need to actually make the subplot. Let's go ahead and run that. So let me run all this, and if that doesn't work, I'm going to finick with it. Yeah, I'm not quite sure why. Oh, you know what? We do need to update the layout so it'll actually display. At least I think that's what it is. Yep, there we go. Oh gosh, I hate that. Template equals plotly dark. There we go, much better. So these are all our different temperature profiles at different positions and different times. Or sorry, really with different positions at different time intervals. And what we want to show is that as we change this time increment, the graph gets weird when we go above 0.5. Let's show what it looks like going below 0.5. Essentially the same, and it should look essentially the same no matter what, as long as you stay below 0.5. But the interesting thing that happens is, let's go really big. Let's go 0.8 and see what our graph starts to look like. Or, you know what? I didn't even show you the other ones because I forgot to run. So the plot stays essentially the same, maybe smooths out a little bit. But as we go above 0.5, you start getting these really, really crazy shapes. And your temperature starts oscillating a lot. And take a look at the number here, 10 to the 159th power. And that's just going 0.3 seconds above 8. Let's do something a little more reasonable, 0.505. And you get these really pretty shapes, but we also know that the temperature along the bar probably isn't going up and down quite like that. So why is that happening? Well, if you want to find out, take a look at the next video. Oh, there's a nice shape.